Large language models and AI agents can generate impressive responses. But how do we know whether those responses are actually accurate, reliable, and safe? Welcome to DataSpeaks, and in this video, we'll move beyond simple vibes-based testing and explore how AI systems are evaluated using measurable, production-grade techniques. We'll cover essential LLM metrics, RAG and agent evaluation, LLM-as-a-Judge, bias mitigation, golden datasets, and continuous production monitoring. By the end, you'll understand not only how to build powerful AI systems, but how to prove that they can be trusted. Let's get started. With that note, let's start with where evaluation began: traditional machine learning. In classic ML setups, we deal with fixed label spaces and deterministic predictions. Evaluating a classification model or a regression pipeline comes down to clear mathematical bounds. Metrics like accuracy, precision, and ROC-AUC give us an objective, ground truth score. However, as we shift toward generative AI, this framework is no longer sufficient.
This brings us to the first big shift: evaluating generative LLMs. Unlike classic ML, LLMs operate in open-ended natural language. In natural language, there is rarely a single correct string. A summary can be written in dozens of valid ways, partially accurate or fluently wrong. Traditional loss functions and binary accuracy fail here because a model can output a response that sounds completely convincing while hallucinating false facts. To evaluate LLMs, we have to move past binary correctness and start scoring multi-dimensional properties like groundedness and context relevance.
When we step up from standalone LLMs to autonomous AI agents, the evaluation challenge multiplies. An AI agent doesn't just generate text, it executes multi-step decision loops. It reasons about a goal, selects external tools, calls APIs, handles runtime errors, and iterates until it reaches a final state. Evaluating an agent isn't just about checking its final output, it's about evaluating its trajectory. Did it call the correct APIs? Did it take redundant steps? Did it recover efficiently from an error? Measuring an agent requires looking at both execution correctness and trajectory efficiency.
Let's look at a concrete case study that illustrates why traditional accuracy fails: the illusion of accuracy. Imagine a user asks, "Summarize refund policy for damaged items." The model returns a smooth, professional response. You can return damaged items within 14 days for store credit. To a human reading quickly, it looks fluent and helpful, but when we audit it against our ground truth documentation using a multidimensional scorecard, it fails across the board. Correctness, fail. The actual policy window is 30 days, not 14. Groundedness, fail. The source document never mentions store credit. It specifies original payment refunds. Completeness, fail. It completely omitted the mandatory step requiring photo proof. This is why single-score evaluation's dangerous in production. Fluency hides factual errors. To fix this, we reimagine classic retrieval and extraction metrics for generative context, starting with precision. In LLM evaluation, precision measures: of all the facts or claims made by the model, how many are actually supported by the source context? High precision means low hallucination. This is your critical metric in high-risk domains like legal contract analysis, healthcare, or financial reporting, where generating a single ungrounded statement carries significant compliance or legal risk.
Now let's pair precision with its counterpart, recall. While precision asks, is what the model said accurate? Recall asks, of all the required facts in the reference context, how many did the model actually include? If a contract summary drops a critical liability clause, your precision might still be 100% because everything it did say was true, but its recall is low because key facts were missed. High recall ensures completeness in auditing, compliance, and automated document extraction. To measure the balance between precision and recall, we use the F1 score, the harmonic mean of both metrics. F1 score equals 2 times precision times recall divided by precision plus recall. Why the harmonic mean instead of a standard average? Because the harmonic mean heavily penalizes extreme imbalances. If a model generates huge amounts of ungrounded fluff, its precision drops, pulling the F1 score down. If it plays it too safe and leaves out critical details, recall drops, also pulling F1 down. F1 gives you a single metric for tasks like JSON schema extraction, form processing, and entity extraction.
Here's when to prioritize each metric in production. Use precision when false information is costly, such as in financial compliance or medical advice systems. Use recall when missing information is dangerous, such as in legal discovery or medical record review. Use F1 for balanced extraction tasks, such as invoice processing, database population, or API payload generation, where both accuracy and completeness matter.
Finally, let's look at the first pillar of a complete multidimensional scorecard: real-world correctness. Correctness answers one core question: is the statement factually true in the real world? Unlike groundedness, which checks if an answer matches a specific provided document, correctness evaluates world knowledge against established facts. In our upcoming slides, we'll build out the rest of this scorecard, covering groundedness, answer relevance, and context recall. Building on correctness, our second dimension is groundedness. Groundedness asks a fundamental RAG question: is the generated output strictly supported by the provided source documents? A statement can be factually true in the real world, but if it wasn't in your retrieved context, it fails groundedness. Measuring this prevents parametric memory leakage and ensures your model relies solely on your internal knowledge base.
The third dimension on our scorecard is relevance. Relevance measures whether the generated response directly addresses the intent of the user prompt. A model might produce a response that is 100% correct and perfectly grounded in the context, but if it wanders off topic or answers a question the user didn't ask, its relevance score drops. High relevance keeps outputs targeted, clean, and actionable.
Moving to dimension 4, we evaluate completeness. Completeness asks, did the model cover every mandatory subpoint and constraint requested in the prompt? This is where high recall meets user expectation. If a user asks for a 3-step action plan with risk factors, and the model only provides 2 steps without mentioning risks, the response falls short on completeness, even if every sentence provided is accurate. Pillar number 5 focuses on safety and policy. Beyond factual accuracy, production LLMs must comply with organizational boundaries. This metric evaluates whether the response passes jailbreak detection, avoids leaking personally identifiable information, and stays clear of toxic or harmful content. In enterprise deployments, an accurate response that fails safety guidelines is an instant blocker.
Finally, Dimension 6 grounds our evaluation in operational reality, cost, and latency. An evaluation framework isn't complete if it ignores system performance. This metric checks whether the generation satisfies your P95 latency SLAs and remains within token budget limits. Evaluating quality alongside latency and cost gives you the complete trade-off matrix needed to select the right model for production.
Thanks, everyone. Now, let's examine a critical nuance in production evaluation, which is groundedness versus correctness. Consider a model response that is correct but ungrounded. Statement might be factually correct in the real-world scenario, but that is not present in your retrieved context chunk. In enterprise RAG system, this indicates parametric memory leak, where model relies on its pre-trained knowledge, but that is not based on your private business data. That's a major risk for the enterprise compliance.
That's great explanation, Ishwar. On the other end of the spectrum, you can have an output that is grounded but incomplete. In this scenario, the model strictly quotes the retrieved context without hallucinating a single word, yielding perfect groundedness. However, it leaves out crucial context required to fully answer the prompt. You get 0 hallucinations, but poor utility and low recall.
To fix these issues, you must decouple your evaluation into 2 stages: retriever and generator. Stage 1 evaluates the retriever. Did vector search actually fetch the necessary source documents? Context recall at k. Measures the fraction of required ground truth facts retrieved in the top k results. Context precision at k. Measures the ratio of relevant signal versus noise in those top k chunks. Hit rate. Checks the overall probability that the target reference document was retrieved. Stage 2 focuses on generator evaluation. Once provided with the right context, did the LLM synthesize it correctly? Here, we measure faithfulness and groundedness, ensuring every claim made is supported directly by the retrieved context. Answer relevance. Confirming the generated answer directly addresses the user's prompt. Semantic similarity. Measuring how closely the output aligns with your golden target answers.
To tie Stage 1 and Stage 2 together, we use the RAG triad framework. The first leg of the triad is context relevance, which evaluates the relationship between the user query and the retrieved context. It answers, did vector search fetch clean signal, or did it retrieve irrelevant noise? High context relevance is essential to prevent prompt dilution and cut down on latency. The second leg of our triad is faithfulness, which looks at the relationship between the retrieved context and the generated answer. Faithfulness measures whether every single statement in the model's response is directly derived from the retrieved chunks. This serves as your strict zero hallucination check, ensuring the model doesn't inject outside assumptions or unverified claims.
To complete the RAG triad, we look at answer relevance, connecting the user query back to the generated answer. Even if a response is perfectly faithful to the source material, it fails if it doesn't actually address the user's original question. Answer relevance verifies that the output hits the target cleanly, without adding extraneous or off-topic text. Now, let's step up to evaluating autonomous AI agents. Unlike standard LLMs, agents operate in multi-turn loops, so we must evaluate the entire execution trajectory rather than just the final output. Stage 1 evaluates planning and intent. Here, we check how effectively the agent deconstructs a user request into ordered subgoals and verify if its step-by-step reasoning remains logically sound and aligned with the target goal.
Stage 2 moves to tool and schema selection. Here, we evaluate whether the agent selected the correct API function for each step and whether it formatted the JSON parameters properly. We measure schema matches and pydantic validation rates to ensure the agent's tool calls are syntactically and semantically correct before execution.
Stage 3 covers execution and recovery. This stage tests how the agent performs when it interacts with the environment, taking actions, observing API feedback, and, critically, self-correcting when an error occurs. Evaluating recovery metrics like self-correction pass rates ensures your agent can gracefully adapt to real-world edge cases instead of crashing mid-task. Here's a hard truth about agentic engineering. An agent that solves a task in 25 turns when it should have taken 3 isn't a success, it's a production liability. Efficiency is reliability. In this stage, we measure 3 critical metrics. Step efficiency ratio. How close is your agent's execution path to the optimal shortest path? Infinite loop rate. Spotting when an agent gets stuck in a death spiral of repeated tool calls. Token cost per action. Tracking the cumulative context cost as turns stack up. In production, every unnecessary turn drains your budget and increases the surface area for failure. Great agents aren't built on happy paths. They're defined by how they recover when things go wrong. In the real world, APIs throw 400s, schemas return invalid data, and rate limits hit. Our resilience evaluation tracks self-correction pass rate, the percentage of environmental errors your agent catches and fixes on its own without human intervention. Tool invocation precision, ensuring parameter payloads are spot on every single time. Circuit breaker trigger rate, knowing exactly when to trigger a hard stop before an agent burns through tokens or executes runaway loops. Resilient agents turn API failures into temporary pauses, not system crashes. So, how do you safely test agents that hold the power to call APIs, write to databases, and execute live code? You don't do it in production. Environment sandboxing is non-negotiable. By mocking external API dependencies and taking deterministic database snapshots, you isolate the agent's execution environment. This gives you reproducible, side-effect-free evaluation runs. You get to test destructive edge cases safely, ensuring your agent behaves predictably before it ever gets the keys to live infrastructure.
To know if your agent architecture is actually improving, you need objective baselines, not isolated test cases. That's where standard community benchmarks come in. SWE Bench, the gold standard for evaluating coding agents on real-world GitHub issues. Gaia, pushing multimodal assistance on complex, multi-step reasoning and tool use tasks. Web Arena, testing web navigation, DOM manipulation, and end-to-end task completion in real web environments. Benchmarking against these industry standards stops you from grading your own homework and gives you absolute clarity on model performance.
Finally, how do we evaluate thousands of complex, non-deterministic agent execution traces? We build trajectory judges. By deploying specialized LLM judges or strict deterministic assertion pipelines directly onto the action traces, we evaluate the entire story, not just the final output. The judge inspects every thought, tool selection, observation, and pivot. It grades logical coherence step by step, ensuring your agent didn't just stumble upon the right answer by luck, but actually executed a sound strategy.
Let's address a major challenge in LLM evaluation. Traditional methods do not scale. Human evaluation is accurate, but slow and expensive. Metrics like BLEU and ROUGE are automated, but often miss semantic similarity when two differently worded answers express the same meaning. This is where LLM-as-a-Judge helps, offering 3 advantages. Scalability. It can evaluate thousands of responses within minutes. Semantic understanding. It assesses meaning, tone, factual consistency, and groundedness, not just matching words. Custom rubrics. We can define company-specific or task-specific evaluation criteria using natural language instructions.
Now, there are 3 common ways to use an LLM as a judge. The first is single answer grading. Here, the judge evaluates one response against a clear rubric, such as accuracy, relevance, or groundedness, and assigns a score, perhaps from 1 to 5. The second is pairwise comparison. Instead of scoring one answer independently, the judge compares 2 responses, Model A versus Model B, and decides which one is better based on the evaluation criteria. The third is reference-based evaluation. Here, we provide an expected or ground truth answer, and the judge measures how closely the model's response matches its meaning. So, in simple terms, we can score one answer, compare 2 answers, or check an answer against a reference.
However, using an LLM as a judge can introduce biases. One example is verbosity bias, where the judge favors a longer answer simply because it appears more comprehensive, even when a shorter answer is equally accurate. To reduce this, set clear word limits and instruct the judge to evaluate quality, not length. The key lesson: a longer response is not automatically a better response.
Along with verbosity bias, we also need to consider positional bias. This bias commonly appears in pairwise evaluation, where the judge compares 2 answers. Sometimes the judge may favor the response shown first, not because it is better, but simply because of its position. A practical solution is to run the evaluation twice by swapping the order of the answers. If the winner changes after switching positions, that indicates possible positional bias. So, the order of presentation should never determine which model wins.
The third issue is self-enhancement bias. An LLM may give higher scores to answers generated by the same model, or by another model from its own family. In other words, the judge may slightly favor outputs that resemble its own style. To reduce this risk, we can use a judge from a different model family, compare scores from multiple judges, or validate the results with a smaller sample of human evaluations. So, LLM judges are powerful, but they should not be treated as completely neutral.
Now that we understand how to evaluate model responses, let's see how evaluation works continuously in production. The process begins with a golden dataset. This is a carefully curated collection of around 100 to 500 representative prompts, along with trusted answers and the correct supporting context. These examples should cover normal questions, difficult cases, and known failure scenarios. Think of the golden dataset as the reliable benchmark we use to determine whether our system is improving or getting worse.
Once we have the golden dataset, the second step is to integrate evaluation into the CI/CD pipeline. Whenever we change the model, system prompt, retrieval strategy, or chunking logic, the evaluation suite runs automatically. If important metrics fall below the required threshold, the deployment is blocked. This prevents a seemingly small change from silently reducing the quality of the production system.
However, passing pre-deployment tests is not enough. Real users may ask questions that our golden dataset does not include. That brings us to step 3, live telemetry. In production, we continuously monitor signals, such as thumbs up and thumbs down feedback, groundedness, response latency, and token cost. This allows us to detect quality problems and unusual behavior under real-world conditions. The fourth step is failure triage. When we identify a failed or low-quality production response, we investigate what caused it. The problem could come from retrieval, the prompt, the model, missing data, or another component of the agentic workflow. After correcting and validating the example, we add it back to the golden dataset. This completes the evaluation flywheel. Production failures become new test cases, and those test cases continuously make the system stronger. For enterprise RAG systems, evaluation can also act as a real-time safety gate. Here, a lightweight model or guardrail judge is placed between the generated answer and the user. Before the response is delivered, it checks whether the answer is sufficiently grounded in trusted documents. For example, if the groundedness score is below 0.9, the system blocks the answer and returns a safe fallback, such as, "I cannot verify this answer against official documents." This interception pattern helps the system maintain strict targets for groundedness, hallucination rate, and retrieval quality, while reducing compliance risk and potential damage to the organization's reputation.
Now, let's connect evaluation with the AI system's level of risk. At the lower risk end are creative tasks, such as brainstorming, marketing copy, and content drafting. Because these tasks rarely have one correct answer, rigid accuracy metrics are less useful. Instead, we evaluate fluency, helpfulness, relevance, and suitability for the audience. The key idea is simple. Our metrics must reflect what success means for that specific use case. Moving one level higher, we have data extraction systems. For example, extracting invoice values, reading PDF forms, or identifying named entities. Unlike creative writing, these systems produce structured outputs with clearly expected values. A missing invoice number or an incorrect dollar amount can directly affect a business process. That is why we use more deterministic metrics, such as precision, recall, field-level F1 score, and schema validation. Here, creativity is not the goal. Consistent and accurate extraction is. Next, we have enterprise RAG systems, such as internal policy search, legal document lookup, or customer support assistance. The answer may sound completely professional and still be wrong. Therefore, evaluating only fluency is dangerous.
We must determine whether the response is supported by the retrieved evidence and whether the retrieval system found the correct information in the first place. This is why groundedness and recall at K become essential. We are evaluating both the quality of the retrieved context and the faithfulness of the final answer.
At the highest risk end, we have autonomous AI agents. These systems do more than generate text. They can call APIs, modify databases, trigger workflows, or initiate financial transactions. For an agent, evaluating only the final answer is not enough. We must examine its entire trajectory, which tools it selected, the order of its actions, whether every step was necessary, and whether it recovered safely from errors. As an AI system gains more authority to act, the evaluation standard must become increasingly strict. Greater autonomy requires stronger guardrails, deeper observability, and more rigorous testing. Now, let's translate that risk spectrum into a practical metric stack for each architecture. For a RAG system, we begin with context precision. How much of the retrieved content was actually relevant? Then we measure recall at K. Did the retriever find the necessary information among its top K results? Next, faithfulness checks whether the final answer is supported by that context, while answer relevance determines whether the response actually addresses the user's question. Together, these metrics evaluate the complete RAG pipeline, from retrieval to final generation.
For autonomous agents, we need a different set of metrics because the system is executing a sequence of decisions. Step efficiency measures whether the agent completed the task without unnecessary actions. Tool call precision checks whether it selected the correct tools with the correct parameters. We also need loop detection to identify agents that repeatedly perform the same action without making progress. Finally, trajectory pass rate determines whether the complete path, from the initial request to the final outcome, was correct and successful. This helps us evaluate not only what the agent accomplished, but also how safely and efficiently it accomplished it. For structured extraction systems, evaluation must be precise. Field exact match checks whether values match the expected output. Precision measures how many extracted fields are correct, while recall measures how many required fields were found. JSON schema validation confirms that the output follows the required structure. Even accurate information can fail operationally if its format is invalid. So, both content accuracy and structural correctness matter. Conversational copilots need both technical and human-centered metrics. User acceptance rate measures usefulness, while sentiment delta shows whether the interaction improves the user's experience. We also track response latency, because a good answer loses value if it arrives too slowly. Toxicity and safety checks ensure the assistant remains appropriate and trustworthy. There is no universal metric stack. The right metrics depend on the system's purpose, architecture, and risk. So, how do we operationalize evaluation? We use two layers, CI/CD gates and production telemetry. Before release, automated tests evaluate changes against the golden dataset. If groundedness, F1, or another critical metric falls below its threshold, deployment is blocked. After release, telemetry monitors live interactions, latency, token costs, and failed responses. CI/CD prevents known regressions, while telemetry catches new real-world problems, creating a continuous evaluation system.
And that brings us to the end of our journey through LLM and AI agent evaluation. We explored evaluation metrics for RAG systems and autonomous agents, LLM-as-a-Judge, evaluation biases, and continuous production monitoring. The key takeaway is simple. A powerful AI system is not automatically reliable. Reliability requires the right metrics, strong guardrails, and continuous evaluation. Thank you for watching until the end. This video was a major collaboration between DataSpeaks moderator Ishwor Bhusal and several expert AI friends. If you enjoyed it, please hit the like button and subscribe to DataSpeaks for more exciting videos. Until next time, please enjoy learning.